Today we're going to learn about free fall and vertical motion. The definition of free fall is any object moving in the air without anything interfering it. We already learned about horizontal motion, as you can think of a car going left or right. And today we're going to talk about vertical motion, so you can think of a rocket moving up or down. But first of all, for free fall, we have two facts. The first one is there's no difference between the acceleration of heavy or light object when it's in free fall. You might argue that a feather falls down slower than a steel, but it's due to uh, air resistance. The second fact is the acceleration is always constant during free fall, and the constant that we used in AP Physics 1 is usually negative 9.8 meters per second squared. So you can look here. We have three balls with different mass. If we ignore the air resistance, they would actually have the same acceleration when falling down. So how was the free fall acceleration calculated? You can actually calculate it at home by setting up an easy experiment. First of all, you can put a ball on the table and measure the height of the table using a meter stick to measure the vertical displacement that a ball would experience. And after that, once the ball begins to fall, you can start the timer and stop the timer when the ball hits the ground. So you know the time interval in which the ball goes through that vertical displacement. Right? And once we collect all of the information we need, we can use a kinematic equation to calculate for the acceleration of the free fall. But first of all, let's make a given list. It's always a good habit to make a given list when you do kinematic questions, especially when you have a lot of variables and values to think about. For final velocity, we wouldn't know the final velocity because we didn't calculate it and it's not given, so we can just cross it off. For initial velocity, though, we know the ball starts from rest in terms of vertical motion, right? You might roll the ball off the table, but that's just horizontal motion. So vertically speaking, the ball has an initial velocity of 0. And acceleration is what we are calculating. We use the stopwatch to calculate the time, so we know the time. And we use a meter stick to calculate the displacement, so we do know the displacement. Since we don't know the final velocity, the only equation we can use is the second one, which is delta x equals to 1/2 at squared plus v0t. And we know that the initial velocity is 0, so we can cross off this term and write a 0. And the delta x just represent delta y here because it's in vertical motion instead of horizontal motion. So delta y equals to 1/2 at squared. We know the displacement and we know the time, so we can just plug them in. And once we have all the information plugged in, the only thing we don't know is just the acceleration. So we can easily calculate the acceleration by doing math. And that's just acceleration of object in free fall. And it should be close to negative 9.8 meters per second squared. Now, what does a graph for object in free fall look like? We can think about the example over here. But in this video, we're just going to talk about the kinematic graph for vertical motion only. And for next video, we might talk about combining the horizontal motion and vertical motion together. But for this video, we can just think about a ball is tossed up and then fell down. Whenever we're doing question for free fall, I like to separate the graph into two parts, when it's going up and when it's going down. So it's more easy to think about it. And I would suggest whenever you're doing kinematic graphs, start with acceleration versus time graph, because again, it's easier to think about. We know, especially in free fall, because we know that it's free fall. And in free fall, the acceleration is always negative 9.8 meters per second squared, or we can just say it's constant. So since it's negative, we know it's negative quadrant. And since it's constant, we know it's zero slope. So we can just simply draw a line in negative quadrant that has no slope, or just draw a horizontal line. The VT graph will be more complicated because we need to consider more stuffs, but we can have more way to think about it. First of all, for the y-intercept, we know that on the VT graph, the y-intercept is v0, or initial velocity. And we know the ball is tossed up, so it has to have some positive velocity to be going up. Since conventionally up is positive and down is negative, the initial velocity has to be positive for an object to going up first, right? So this is positive, and we draw a point in the positive quadrant for the initial velocity. And from here, we can have two ways to think about it. The first way is just using slope. We know the slope of VT graph is acceleration, and since acceleration is constant, we know that its slope is constant as well. And we would just have two choices or two options for a constant slope. It's either this or this, right? And we know that originally when it's going up, the velocity is positive and the acceleration is always negative. The velocity and acceleration is going opposite direction. So that tells us the ball is slowing down. Then we know the y data point is actually getting closer to the x-axis when it's going up. So we would know that it's this shape. However, we can also just not think about the slope and just use the y data point to think about it. So on the other hand, when it's going down, we know the velocity is negative and the acceleration is also negative because the acceleration is always constant. If velocity and acceleration is going at the same direction, then it's going to speed up. Right? So for this first part, we know that the y data point is getting closer to the x-axis. So it will look like this. And what's more, for when the ball is going down, it's speeding up, so the y to the point is getting further from the x-axis, like this. So again, we get a graph like this, downward sloping. Now from observation, you might see that at the highest point of free fall, when it's tossed up, you would have a velocity of 0. This is actually an important physics fact to know, especially when you're dealing with free fall and projectile motion. So the max height is 0. The max height is when the velocity is 0. Okay, so now we're just gonna think about YT graph, or vertical position versus time graph. We also have a lot of way to approach the YT graph. First of all, the initial position is really not given, so it could just be 0 to make it easier to think of. And we know the slope of this graph will just be velocity. And when it's going up, the velocity, the data point is in the positive quadrant, so it's moving up. And since it's going in the positive direction, we would have a positive slope on this portion when it's going up. However, we also know that from here, it's slowing down. So when it's going up, we have a positive slope. We have a positive slope, but the slope is decreasing since the velocity is decreasing. So what does it mean by decreasing slope? You can just think of it as the slope is getting more flat. So originally it's steep, but it gets more flat. So if you make it continuous, it will just look like this. On the other hand, when it's going down, we know the direction is to the negative. So we would have a negative slope. And since we know it's speeding up, the slope would be increasing. And what does it mean by increasing slope? That just means the slope gets steeper. And since it's negative, it goes down like this, right? So now we have the 3 kinematic graph when it's in free fall. It's only in the situation when something is tossed up and fall down. Okay. Now I have 2 practice questions. We can go over them together. You can pause the video if you want to try it first. The first question is, a person climbs up to the roof of the school 13.2 meters above the ground and throws a ball straight down with an initial speed of 19.4 meters per second. So first of all, we need a given list. We know 14.2 meters is the displacement. It's in free fall, so negative 9.8 meters per second squared. By the way, since it's going down, the displacement is also going to be negative. And the initial velocity is negative 19.4 meters per second because it's going down. And the final velocity is what we are calculating. We actually don't know the time in this question. So if we don't know the time, we cannot use the first two equations. So instead, we're going to use the third equation. So v squared equals to v0 squared plus 2a delta x. And for now, we can just plug in whatever we had. It's just final velocity is what we are calculating, and we plug in the initial velocity, which is negative 19.4, and we squared it, plus 2 times negative 9.8 times the displacement is negative 14.2. And if we simplify all of them, we get v squared would equal to 654.98, and v, you can just square root both sides, and the final velocity would just be 25.59 meters per second. But remember, it's going down, so we need a negative sign. Directions matter. And the second part of the question tells us to draw a YT graph and a VT graph. We can start with a YT graph. Or a VT graph. So for the YT graph, we know it starts from a place that's above the ground, so it's gonna be positive, right? So the y-intercept would be positive, and the velocity is positive. The velocity is negative. The acceleration is also negative. So speeding up, right? Because same direction. And since the velocity is going to the negative direction, we know it's downward sloping. So it would look like this. On the other hand, for the VT graph or VYT graph, we know that the initial speed is 19.4 meters per second, but it's throwing downward, throwing straight down. So if it's throwing straight down, that means the velocity is negative. Since the initial velocity is negative, we would know that the initial velocity or the y-intercept is negative. So we can assume it's here, right? And again, speeding up, y to the point getting further from the x-axis. So it will look like this. And by the way, the acceleration is constant, so it will be a constant slope. Okay, now let's look at the second question. Is that a tennis ball travels straight up in the air, reaches a max height of 4 meters and has an initial throwing velocity. The tennis ball is thrown into the air again, and this time reaches max height that is 3 times larger. By what factor does the initial velocity of the tennis ball changes? So we can write a given list. For this question, we are asked about the factor. So the actual value doesn't matter. What matters is the factor, right? We know it's in free fall, so the acceleration is always negative 9.8 meters per second squared. So the factor doesn't change. The factor is always 1 for acceleration, right? And the max height is 3 times larger. So the factor for the max height or the displacement is 3. We don't have any information about the time, so we can cross out the time. V0, we learn from here. At max height, the final velocity. At max height, the final velocity is always 0. So it's just 0. And the initial velocity is what we are calculating. What factor does the initial velocity of the tennis ball changes? So we gather all the information, and we can see there's no time. So we use the third equation again. And we can just cross off this term because it's 0. And now we get 0 equals to the initial velocity plus 2a delta x. But since the ball is traveling straight up, the displacement here is positive. But the acceleration is negative. So instead of plus here, we can write it as minus to avoid confusion. So we plus 2a delta x on both sides. It becomes 2a delta x equals to b0 squared, and we now plug in all the things we have. Remember, 2 is a constant, right? 2 is a constant. So when dealing with factor, the 2 is always that 2. It doesn't change when the height is 3 times larger. So when we are plugging the factor, 2 remains. So it's always 1 times larger, right? 2 is 1 times larger than 2. So the factor is 1. For the acceleration, we know the factor is 1 because it doesn't change as well. And we know the displacement is 3 times larger, equals to initial velocity squared. Now, if we rearrange the initial velocity equal to initial velocity squared equals to 3. So the factor of the initial velocity is root 3. So we need an initial velocity of root 3 times bigger in order to get a max height that's 3 times larger. Alright, thanks for watching. Next video, we're going to talk about projectile motion. Yeah, we're all down. See you next time.